Good day, everybody. How are you doing? Today we are going to talk about material for week 12. So without further ado, let's get started. Test for independence and homogeneity, section 10.2. Interpret contingency tables, perform test of independence, perform test of homogeneity. Okay. Interpret contingency tables. Okay. Do some college majors require more studying than others? Table below shows the results from National Survey of Student Engagement Survey, where a sample of 1,000 college freshmen were asked their major. So their majors are on the vertical columns, okay, like humanities, social science, business, and engineering, and the average number of hours work per week spent studying. So there are three categories of those: 0 to 10 hours, or first row or horizontal line. Second row is 11 to 20, and the third row is more than 20. So this table is called a contingency table because each student is classified based on their major and how many hours per week they study. So when a person or an individual or an object is categorized into two categories, it is called, and data collected, this is called a contingency table. A contingency table relates two qualitative variables. On one of the variables called the row variable has a category for each row of the table, which in our case is hours studying per week. The other variable called the column variable, in our case the major, has one category for each column of the table. The intersection of a row and column, for example, intersection of humanities and the first row, 0 to 10, is 68. That means out of 68, out of 1,000 students, 68 students had humanities major and they studied 0 to 10 hours per week. So that is cell. That is a cell. The total number of individuals in the table 1,000 is called a grand total. Perform test of independence. We are interested in determining whether the distribution of one variable differs depending on the value of the other variable. If so, the variables are dependent. What does it mean in this case? That is, if for a particular measure they spend more time, okay, then they are dependent. If the distribution of one variable is the same for all values of the other variable, the variables are independent. So it does not matter in the second case, if they're independent, it does not matter what their measure is. They're approximately studying about the same hour. Then they're independent. What are independent? The hours they spend studying and their measure are independent. In the survey about measures and hours spent studying, if these variables are independent, then the distribution of hours studied will be the same for all the measures, and the distribution of measures will be the same for all categories of hours studied. If we are to conduct a test to determine if the two variables in the previous survey about student measures and hours spent studying are independent, the null and alternate hypotheses are: the null hypothesis, hours studying and measure are independent. Alternate is hours studying and measure are not independent. So independent is the null hypothesis, is the status quo, and alternate or test hypothesis is hours studying and measure are not independent. We will use chi-square statistic to test the null hypothesis that our studying and measure are independent. If we reject H0, we will conclude that the variables are dependent. Okay. So in each case, we have to find first the row total. So there are three row totals. That's on the last column. And also we need to find each column total, which is in the last row. And there are four of those. Now, if you add all the row totals in the last column, you will get 1,000. Also, if you add all the column totals in the last row, 257 plus 261 plus 309 plus 173, you get 1,000. Now, the null hypothesis states that the hours studying and measure are independent. By using the multiplication rule for independent events, we can compute the expected frequencies, that is, if they're independent. For example, probability of studying 0 to 10 hours and humanities. Okay, 0 to 10 hours and humanities. So what percentage of the people are studying 0 to 10 hours? 345 out of 1000, because 345 is the sum of the first row, which is 0 to 10 hours. And what percentage of the people are humanities? The total of humanities, the first column is 257 out of 1000. So probability of studying 0 to 10 hours and probability of studying humanities is the product of two individual probabilities, because we assume they're independent, which is the null hypothesis. So we multiply the two probabilities. Now to obtain the expected frequency for those who study 0 to 10 hours, or expected count, and a humanities measure, we first multiply the two probabilities to get the probability of both humanities and 0 to 10 hours. Then we multiply it by the total sample size, grand sample size of 1000, to get the expected count in the first cell, first row, first column, which is intersection of 0 to 10 hours of studying and humanities, as 88.665. So from the previous example and applying some arithmetic, we can see that each expected frequency can be obtained by the following formula: row total times column total divided by grand total. The expected frequency for a cell represents the number of individuals you would expect to find in the cell under the assumption that the two variables are independent. If the differences between the observed and expected frequencies tend to be large, we will reject the null hypothesis of independence. Okay, so what is step one? State the null and alternate hypothesis, compute the row and column totals, compute the expected frequencies. Expected frequency is row total times column total divided by grand total. Now check to be sure that all expected frequencies are at least 5. Choose a level of significance alpha and compute the test statistic chi-square, okay, which is the difference between observed and expected. Then you square that difference and divide it by the expected frequency. Then we add the sum of all this. Okay, find the critical value. Degrees of freedom is rho minus 1 times c minus 1. So r minus 1 means rho minus 1. So if there are 3 rows, it's 3 minus 1 is 2. And if there are 4 columns, 4 minus 1 is 3. So 2 times 3, 6, for example, degrees of freedom. And degrees of freedom, where r is the number of rows, c is the number of columns. If chi-square is greater than the critical value, reject the null hypothesis. Otherwise, do not reject H0. State a conclusion. So the null hypothesis, studying and measure are independent. Okay, our studying and measure are independent. Alternate is our studying and measure are not independent. How to do this in the calculator? So I'll work with you. So these are the observed values. Okay, so first we put the calculator on, then press the second button on the top left, then plus on top of enter, then number 4. Clear all list, hit enter again. Done. Okay, now we are going to enter the observed values. Where do we do? We do not do it in L1 or L2. We have to do it in a matrix. Notice we have 3 rows in this data and 4 columns. Okay, 3 rows and 4 columns. Okay, 3 rows and 4 columns. Okay, so first we have to find out where the matrix is. Second, press the second button and then X minus 1, matrix button. Okay, then second X minus 1 gets us the matrix. On the top row, go to edit. Okay, and then press number 1. The first number is the number of rows, which is should be 3. Okay, so 3, then hit enter, goes to number of columns. Here we have 4 columns: humanities, social science, business, and engineering. So make it a 3 by 4 matrix. Okay, now we are going to enter the observed values in matrix A. So first line 68, enter, 106, enter, 131, enter, 40, enter. Okay, then we go to the next row, 119, enter, 103, enter, 127, enter, 81, enter. Then 70, enter, 52, enter, 51, enter, 52, enter. So we have entered all the observed values in matrix A. Okay. Okay. Now these are the expected counts. Remember, expected counts are of row total multiplied by column total divided by grand total to get these numbers. So let's press again second and x minus 1. Go to edit on the top row, then number 2, because now we are going to enter the expected counts in matrix B. So go to number 2 and make it a 3 row. First number is number of rows, 3 rows by 4 columns. Okay. So let's enter the values of this. So the first number is 88.665. Next one is 90.045. Next one is 106.605. And next one is 59.685. Okay. Go to the second row, 110.510, 112.23, 132.87, and 74.39. Next row, 57.825, 58.725, 69.525, and 39.925. Okay. So we have entered the expected frequency or expected counts in matrix B. The observed counts are in matrix A. Now we are ready to do the chi-square test. So stat, then highlight test on the top row, then scroll down under test to go to chi-square test, not the chi-square GOF test. Chi-square test. This is the first one, chi-square test, hit enter. My observed is A, my expected is B, and I scroll down to calculate and hit enter. My chi-square, which is the test statistic, that is a characteristic of the sample that we have that we have collected, is 34.637. But the interesting part is to look at the p-value. P-value is not 5.06, it's 5.06 e minus 6. That means a decimal followed by 5 zeros and then 5. That value is much, much less than alpha equal to 0.05. So p-value is less than alpha, decision reject 80. And we conclude that at alpha equal to 0.05, there is enough evidence to support the alternate that row and variable and column variable are not independent. That means what? That means depending on your major, you will study more or you study less. So basically your major determines how many hours you study per week. Yep. So their chi-square test statistic is 34.638. They compare it to the critical value with 6 degrees of freedom. We have DF equal to 6. Why 6? Because remember it's row minus 1 multiplied by column minus 1. We have 3 rows. So row minus 1 is 3 minus 1, 2. And column minus 1, we have 4. 4 minus 1 is 3. So 2 times 3 degrees of freedom is 6. Okay. So they show you how to get the chi-square stat test, and then you scroll down to chi-square test. Okay. How to enter the data. Matrix A contains the observed data and matrix B contains the expected data. Okay, so here is another problem you can do. Okay. And then the next is perform test of homogeneity. In the contingency table we have seen so far, the individuals in the table were sampled from a single population. For each individual, the values of both the row and column variables were random. In some cases, values of one of the variables, say the row variable, are assigned by the investigator and are not random. In these cases, we consider the rows as representing separate populations, and we are interested in testing the hypothesis that the distribution of the column variable is same for each row. This is known as a test of homogeneity. In a test of homogeneity, we are testing the hypothesis that the distribution of outcomes is the same for each row. The method for performing a test of homogeneity is identical to the method for performing a test of independence. Can you conclude that the distribution of outcome differs among the treatment groups? So there are three treatment groups, T only, R only, and both drugs. In the example with the drugs, the T drug and R drug. Okay, so the null hypothesis is says that the distribution of outcomes, the result, which is fatal heart attack, non-fatal heart attack, and no heart attack, is the same for all drug treatments. What are the three drug treatments? T only, R only, and both drugs. Null hypothesis, distribution of outcomes, results, is same for all kinds of, for all the drug treatments. The alternate hypothesis says that the distribution of outcomes is not the same for all the three treatments. Okay, so just like before, we have to calculate the expected counts in each cell by multiplying row total. For example, for the first row, it will be 8542 multiplied by the column total 1821 divided by the grand total 25620 to get the expected count in cell 1, which is row 1 and column 1 is 607.14. Just like before, we have to enter the observed counts in matrix A and the expected counts in matrix B. So again, we go to second, then x minus 1, which is in the first column, and then edit on the top row, then number 1. This time we are interested in a 3 by 3. The first number is the number of rows, which is 3 over here. So we go to the second number. Instead of 4 columns, we now want 3 columns and hit enter. Okay, so now we enter the observed counts in the first row, 598, 431, and 7513. In the second row, 603, 400, and 7573. In the third row, 620, 424, and 7458. Okay. Now we again press the second button and x minus 1. Edit. And then we go to number 2. Make it a 3 by 3 for expected counts, 3 rows by 3 columns. And now we enter the data from for the expected counts, starting with the first row, 607.14, 418.43, 7516.43, then 609.56, 420.10, 7546.34, then 604.30, 415.47, and 7481.23. So that's the expected counts all entered in matrix B. Now we go to stat, highlight test. Okay, so remember the null hypothesis, the outcomes are same for all the treatments, and outcomes are not the same for all the treatments, the alternate. Okay, then the distribution of outcomes is the same for all the drug treatments, alternate the distribution of treatments not the same. So we will do a chi-square test. So stat test and scroll down to chi-square test. Okay, stat, then test, and scroll down to chi-square test. Okay, which is C. Charlie is the chi-square test. So hit enter. Observed is matrix A, expected is matrix B. Calculate the test statistic. Enter. Chi-square is 2.259 and the p-value is 0.688, which is greater than 0.05. Decision, do not reject 80. Okay, and we can conclude at alpha equal to 0.05. There is not enough evidence to support the alternate hypothesis. Yes. Okay. So that's it for today. If you still have questions, you can always shoot me an email. I'll get back to you as soon as possible. Thanks for watching and see you next time. Take care. Have a nice day.